screening of low lattice terminal conductivity compounds using active learning. And we just had this very nice presentation where we talked about the problem of thermoelectrics. So in thermoelectrics, we have a lot of competing criteria. Like if you have the set T expression up there, you have to have a high Seebeck coefficient. The electrons, heat needs to make the electrons conduct in one way and not the other way. We have to have a low, we have to have a high conductivity, and we have to have a low lattice thermal conductivity and a low electronic thermal conductivity. So we have many different criteria, and a lot of compounds have rather high lattice thermal conductivity. But I mean, generally is that, well, all these other criteria, they are a bit, they're very interlinked. But in any case, we need low lattice thermal conductivity. So that was our motivation for trying to make a machine learning algorithm to predict lattice thermal conductivity. Okay, but first of all, why do we need a machine learning algorithm? DFT is excellent. Well, if you look into how you compute the lattice thermal conductivity from DFT, you'll find it's pretty expensive. I mean, the kappa, the lattice thermal conductivity expression is up there. And well, some of the parts like the heat conductivity, heat capacity per mode and the phonon velocity is not that expensive to compute. But if you want to include a three phonon scattering, that requires many big supercell calculations. And we used such DFT calculations to generate the lattice thermal conductivity. And we were able to do it for roughly 200 compounds before we kind of like, now we have to stop because we're using so much computer resources. So now we heard in the previous talk as well about, you know, the material space being big. Of course, it's much bigger than 100,000, but 100,000 is roughly the amount of materials you can readily screen. And we could do around make a training set of around 200 compounds. You see here is a huge mismatch between what we would like to screen and the number of training data we can generate. So first of all, we just wanted to analyze this problem a bit. So we did a pure case study for Hauff-Häuslers. We calculated the lattice thermal conductivity around 130 materials. And then we made a training set of 40 compounds. And then we tried to predict and compare with what DFT said. And you can see here that you can very easily end up in a situation where these rare low lattice thermal conductivity compounds are not covered. You see here, for instance, thanks a lot. You see here that in these regions with relatively high, medium to high lattice thermal conductivity, there's an excellent agreement between theory and experiments. Then there are these 5-6 compounds which happen to not be in the training set, and we are not able to predict them as low lattice thermal conductivity compounds. Of course, this has part to do with the fact that we use random forest. A different algorithm might be better for it, but the problem is generic. The rare compounds would not be covered by a random training set in many cases because they are rare. And if you just did, yeah, I could use a pointer, sure. Okay, thank you. Yeah, so if then, yeah, this was this difference I talked about, in case that was confusing for you. If we do the principal component analysis of this, we could very easily understand why. So in the principal components, these are the two most important principal components. We see that all these low lattice thermal conductivities fall out of the span, essentially, of our training data. So one way to deal with this is just to, well, let's just include those compounds that are far away from our training data. So we basically, well, we had this pool here in the PCA space, and well, this one was very far away, so we included that, and we included 2 more. And then we got, well, a radically improved prediction with the machine learning model. Because we included this training data, the predictions for the 2 remaining low lattice thermal conductivity compounds got very accurate, or rather accurate. accurate enough that we can identify that these are low lattice thermal conductivity compounds worth exploring further. So that was the case study. So our scope was not these 100,000 compounds. We were limited. We thought we should limit ourselves initially to the 1,700 cubic materials in the materials project. Of course, not all of these are synthesizable, as we heard earlier, but this was our starting point. So that would be the next question, you know, if they are synthesizable. And then, as I said before, we can compute for about 200 of these compounds. And here's the entire list of space groups and compounds among these cubic compounds with 2 to 7 atoms. Okay, so we could maybe continue here with the PCA method, but that's an inherently linear method, and we didn't really believe these kind of systems are linear enough. So of course, then we picked up that in machine learning force field, people use Gaussian process regression. So maybe we could try that for our systems as well. And as you know, in Gaussian process regression, it's very suited for active learning, because you could pick that compound with highest uncertainty and put that into the training data, and then you improve the model significantly. So here's just an example. Many have probably seen a figure like this before. This is the Gaussian process regression uncertainty. You put in the highest uncertainty compound, and then or data point, and then you improve the model a lot. Okay, we also thought a bit ahead. We wanted to make features that didn't require any DFT input, not even relaxations. So we just used the crystal structure and atomic features for this. So for instance, we found in particular the Voronoi surface to be a very useful way of constructing features. For instance, the face area of the Voronoi surface and the perimeter area scaled in relative to the size of the atoms. And of course, all these atomic features. And then to avoid having to use maximum, minimum, which wouldn't be scalable to very larger systems, we used like standard deviation and median and so forth of the various atoms we included. Okay, so first we wanted to test this approach, whether it was effective. So we did another case study where we just calculated for 200. Basically, we took a initial training set of around around 250 T-depth calculations for lattice thermal conductivity, and we split it in 3 pieces. We had a test set of 20, which we kept fixed. We made a training set of 108 and a training pool of 108. That's the other way around. Yeah, training pool of 110. So then we gradually move stuff from the training pool to the training set, and we compared 2 different approaches. We did the random selection here. That's what you see in blue here. This is from the cross-validation, how much uncertainty we have. And the green one is the R2 score when we actively selected the high uncertainty compounds. So there's a radically improved convergence, essentially, of the training set. For instance, here initially we get a huge improvement, and then when we get essentially reach convergence after adding 40 additional compounds. So the approach seems to work. So we then extended it to this entire set. So we now have a not the training set, but we have a screening set of around 1,500 compounds. And you see all these blue dots there, that's the high GPR uncertainty compounds. And then we add in these 30 actively sampled compounds. And then you basically see how the predicted GPR uncertainty goes drastically down. And we can continue this procedure, adding in more the highest uncertainty compounds. I should mention that, well, we added 30 compounds in total. Roughly half of we actually had to screen over 60 compounds because half of them turned out to be dynamically unstable. So there is a very close link between dynamical instability and low lattice thermal conductivity. So that was quite interesting. In practice, it's a bit tedious to add in one compound at a time. Though there are big calculations, you still kind of lose track of it if you just have to add one compound a week into the system, into your machine learning method. now into the DFT calculation. So we did this in blocks of 15 elements, of 15 compounds. So then we see how this GPR standard deviation goes down, but then we retrain the model with the new data, and it jumps back up again because the model gets wiser, and then we retrain, and so you get a gradual improvement, but you do some errors, and you maybe not pick the best compounds in the immediate time in between. Another interesting thing that happened here, as you might remember, we calculated a lot of Half-Oysters first, and then we looked at, so this have initial data set of 122 Half-Oysters, that's what we did, and then we had 61 left. Here the model didn't want more Half-Oysters, it was quite tired of Half-Oysters, it needed it had what it needed to have low uncertainty for those compounds. But for instance, for the Lewis compounds here, there were no of those systems in the initial data set, and it included 7 more actively sampled compounds from that, because it was clearly undersampled. You also see this in the distribution of lattice terminal conductivity on the left here, that we had a lot of medium, large lattice terminal conductivity, and we also initially added in some low lattice conductivity, so those were quite well sampled. But then here, moderately low and something here like quite low lattice terminal conductivities were completely missing essentially from the initial data set, and basically the training set got very much rebalanced when we did this active learning. So we have a much better training set in the end. Another bit interesting thing is that from our validation, the R2 score actually went down with more data. It's because, well, the data, well, it was very confident. Then it got in some difficult data, and the confidence got slightly down. But then we tested on for realistic compounds, or for compounds that were of interest. Here's a couple of low lattice terminal conductivity compounds that have been reported in literature before, or this one we computed ourselves. And we see here that the initial model could predict 2 of these to be low lattice terminal conductivity, but these 2 compounds here would not be interesting for terminal conductivity, because our lattice terminal conductivity was a bit too high for what you really want for thermal electricity. And then the active learning model reduces this drastically, and it then agreed very much with the reference we found in literature. So this is not exactly the same, because not all of these are based on TDEP, so they differ slightly. This is not supposed to become this even with a perfect model, because it's literature data. Okay, going through Matteo's project, we then found 30 compounds with lattice terminal conductivity below 1.3 watt per meter Kelvin, which are all very good values for thermoelectric applications. 13 of these have been reported before, and we found 17 new. Of course, again, some of these materials are just listed in Matteo's project, might not be synthesizable, but well, we have a good starting point of which systems we should then do further DFT calculations on, and to also assess for electronic properties. And here's the list of compounds that might be of interest. And it's quite interesting when we looked at the features. We also found that the big electronegativity difference was maybe the most important feature. And you can also see that here in the way the band structure looks like. And if you look at the atom projected density states, you see here that the thallium is essentially just vibrating, is rattling. All the 3 atoms are essentially rattling. They just vibrate independently, more or less here, which was an interesting result. Okay, I come to my summary here. So I first showed you a PCA-based assessment showing, we really need to actively put in compounds far away in feature space. It will be necessary to really discover these rare compounds. Then we showed how Gaussian process regression can be used in a systematic way to enlarge the training set and therefore improve the model systematically. And we found then 17 new compounds with a very low lattice terminal conductivity, and many more that had quite low lattice terminal conductivity. Screening these 1,500 compounds, and we of course hope to extend this further to other compound classes and also more compounds that might not be listed in materials project. Okay, thanks a lot for listening.
Thanks a lot, Kristian. Other questions? I already see the first one. So
very good talk. Thank you very much. Very good talk. Thank you. So one of your training set data, like your information that you give the model, is the structure.
Yes.
So many thermoelectric materials go through a structure phase transition. For example, germanium telluride.
Yeah.
There is one at around 400-500.
Yes, and then for germanium telluride also, that's why we didn't want to do just atoms, because the structure really, I mean, the space group matters, how the way the atoms pack matters. But we didn't include the lattice constants in it. We just included the way it packs.
So that's exactly my question. How is this accurate? Because if you just have structures, if you just have the structure, how is this accurate? How would you predict, say, thermoelectrics at 400 Kelvin? Because you have a wrong.
Oh, we only predicted for our training data is for 300 kelvins. That's what we went for. I mean, our goal is to find low lattice terminal conductivity compounds.
Only at one temperature.
We only did one temperature. We thought that was a more fruitful way of working. I mean, I see that other people are working on many temperatures at once to, expand the training data or something. But our goal is to find low lattice terminal conductivity compounds.
And most of the time it does go by 1/T anyway. So
yes, I mean, usually these curves are quite boring unless they include a lot of fancy scattering or something. Yeah.
Oh, thank you.
okay, are there other questions? So I had while you ponder this, I had a question. So you showed R-square curves a lot. I can't remember if you showed also errors on the conductivity that you were trying to predict.
No, I mean, this is one example here. No, I didn't really show that. No, I mean,
so especially in this sort of low conductivity regime that you're aiming for, how predictive is your model then, especially when you're looking for outliers, as Tonio put it?
Yeah, well, I have this case. I mean, we basically went two ways around this. I mean, first we had the case study on half-Heuslers, where this is a log plot versus TDAP calculated data.
Yep.
So I guess if you can do exponentials quickly in your head, you can see an idea of your accuracy. And we had this reference study here with literature. So of course we didn't aim to get exact same values, but here in this case it's around 30% accurate or something for these systems. Yeah.
Are there other questions? Is there anything on Zoom? Not on Zoom. Okay, I see no further questions. Well, the speaker will be around for the whole workshop, so you can always approach him in a coffee break. So
yeah.
Thanks a lot, Kristian.
Thanks a lot.
Now we come to our last invited talk for the day. I've seen Maria online already.